Yeah, I'd like to thank the organizers for this very nice conference and for the opportunity to speak. So already in this conference, we've heard a lot about how gravitational waves are revolutionizing our understanding of the astrophysics of black holes and neutron stars. So my talk, I want to focus a bit on how we can use gravitational waves as probes of new physics. So I'm going to give two examples of that. One is looking for modifications of general relativity, and so this will follow directly from Harvey's talk earlier this morning on doing full numerical simulations of compact object mergers in the specific class of modified theories that give you second-order equations of motion. And then the second example of probing new fundamental physics that I want to also mention is looking for ultralight bosons using this phenomenon of black hole superradiance. And sort of a theme of this talk is that we're already beginning to probe these things using the gravitational wave observations, but the theory is kind of lagging behind in the sense that we could be doing better, we could keep getting better constraints, and we can, if we basically have a better understanding of what's happening in the nonlinear and relativistic regime. And so in that sense, there's more work for the theorists to do, even though we've already made a lot of progress through the contributions of a number of researchers in this field. So just as a demonstration of kind of this exciting era, we're actually able to test general relativity using gravitational wave observations. I have some results from the previous round of the LIGO collaborations, or LIGO Virgo collaborations test of general relativity using the second gravitational wave transient catalog, and actually the third catalog results are already on the archive, which you can see in this preprint here. But I just wanted to highlight a couple of the tests that they're doing. So it's things like varying post-Newtonian and phenomenological coefficients, looking for Lorentz violating coefficients, mass of the graviton, or deviations away from the curve frequency. So it's very exciting that we're able to do these tests with this completely new way of looking out into the universe with gravitational waves. However, you could say that a lot of these tests are sort of against strawmen in the sense that for a lot of these deformations of general relativity, we don't actually have a consistent theory that would give you these deformations, and that's kind of for good reasons. In the sense that there are actually very few modified theories of gravity that are sort of on the same theoretical footing as general relativity, in the sense that it can give you a complete answer to, for example, what happens when two black holes come together and merge. So in this talk, I'm going to focus on a subset of theories where you can actually solve the equations fully non-linearly. So in part, that's kind of due to my personal research style, which tends to focus on numerical GR type simulations, but it's also motivated by the fact that these theories will be the ones that we can constrain the most, and maybe even more importantly, I think it's important to have example theories that we can get predictions from, both to sort of motivate more theory agnostic tests and make sure we're actually testing things that can be realized, at least in principle, and also to sort of benchmark more approximate methods that are being used to go after these modifications to general relativity. So in some sense, the theories that I'm going to talk about might also be considered strawmen of sorts. Like Harvey is mentioning, there's not a really compelling reason to think that there's new gravitational physics at a kilometer scale. But at least these sort of strawmen can sort of walk and talk in the sense that they can give you a full answer to, for example, what happens when two black holes merge. In Harvey's talk, he kind of already went over this, so I'll just be very brief here. But we think of modifying general relativity by adding extra terms to the Einstein-Hilbert action. And here, for example, I'm just considering adding one additional scalar degree of freedom. There's a whole zoo of possibilities we can consider. So some terms like the Riemann to the third or Riemann to the fourth type terms that, for example, Claudia was talking about yesterday, when you vary the action, you no longer get second order equations in motion. And for those kinds of theories, it seems very hard to actually get a well-posed formulation for them. And so you're kind of really forced to treat these theories as approximate and valid over some length or time scales. There's a subclass of theories where you do get second order equations in motion called Hordinsky theories. And we can still think of motivating these theories, as Harvey explained, through some effective field theory type arguments. But with second order equation motions, there's some better hope of getting a well-posed formulation, though, as Harvey told us, you really need the right formulation to do that, which was something that was only sort of come up with in the last couple of years. So I want to mention a couple of the different approaches that people are using to go after modifications to general relativity and to sort of treat them as some deformation to a usual numerical GR type simulation. So one approach is this order reduction approximation, where you basically take your modifications to GR and you solve for them order by order in some small coupling parameter. And the advantage of this is that at each order you have the same principal part as the Einstein equations or the Klein-Gordon equations, so that they are well posed. But sort of the downside is that, as Masha Konkova and her collaborators have shown, is that once you go beyond the test field level and start solving for the metric perturbation that you get from these modifications to GR, then you begin to accumulate errors that sort of due to secular effects. And so in that sense, and these secular effects sort of accumulate on the radiation reaction timescale, and so that makes them very difficult to use to give you predictions of how they would alter gravitational waves, for example, from binary black holes. An alternative approach that Louise and his collaborators have been going after is to basically sort of introduce ad hoc modifications to some theory to the short wavelength behavior to basically make the theory well posed while still having the correct long wavelength behavior. So that gives you a well posed formulation and can potentially cure these problems with secular accumulation of errors. But sort of the challenge there is that you have to ad hoc introduce some short time scale, and you want to make that time scale sort of sufficiently short that the answer you get doesn't depend on it, but not so short that your computation becomes sort of intractable. And then the third approach that I'll be talking about is to just solve the full equations. So that's nice in the sense that you don't have any approximations to justify, or you have to worry about not including some non-perturbative effects. But that really restricts you to studying theories that have some well-posed formulation, and that restricts you both to specific theories and specific parameters. And you're really sort of working without a net in the sense that if your evolution wants to take you into some regime where the theory breaks down, then things go flat, and you can't continue the computation. So I don't have to go through this in detail because Harvey just explained this to us this morning. So this is just my one slide to remind you of what he said. But so the way we're sort of solving the full equations is to use this modification to the generalized harmonic formulation that Aaron Kovacs and Harvey came up with. And the basic idea is you introduce these two auxiliary metrics, one of which determines the light cone for the constraint propagating modes, and one of which determines the propagation of the gauge modes. And if you choose these auxiliary metrics to be distinct from each other and the physical metric, then for sufficiently small couplings in front of your modified gravity terms, that is that they're small compared to all your relevant length and time scales, then you're guaranteed to have strong hyperbolicity. So when we saw this new formulation, my collaborator Justin Ripley and I were pretty excited, and we wanted to try it out. So first, I'm just here showing you some weak field tests that illustrate in practice this problem with not having strong hyperbolicity that this formulation was designed to fix. So on the plot on the left, you can see basically what happens when you make some small perturbation to your initial conditions. And these different curves correspond to perturbations at higher and higher frequencies you get by going to higher and higher resolutions. And what you can see is that these perturbations actually grow faster and faster in time. So in this case, you won't be able to converge to some solution. So that's just with a plane harmonic formulation. But then when you switch on these auxiliary metrics, then that problem goes away. So that's a nice sort of test case. But of course, the question that we're most interested in is, can we apply this to sort of the physically interesting case of black holes merging and cases where the gravitational wave signal would actually be modified by having these modifications to general relativity. So that's kind of the question that Justin and I set out to answer. So we decided to focus on the particular case of Einstein's scalar Gaussbonnet. So it has this action here. You have a scalar field coupled non-linearly to the metric through this Gauss-Bonnet curvature term. And you can consider different forms for this coupling, but in this talk, I'm just going to focus on the simplest shift symmetric form. And so this is sort of a representative example of a Hordinsky theory that differs from GR qualitatively in a couple ways. For example, one is that it violates the null convergence condition. So black holes can actually have their area decrease in this theory. The equations are now fully nonlinear. And as Harvey mentioned, this particular theory has attracted a lot of attention because it can give rise to black hole solutions that have scalar hair. And so it can give you interesting phenomenology in the strong field regime while sort of evading these weak field tests. And because of that, there's a lot of results in the literature on like the PN expansion, studying stationary black hole solutions in this theory. Those in particular found that if you have a certain black hole mass, then as you turn up the coupling parameter, you can only make it so high before you no longer find stationary black hole solutions in this theory. And we can also leverage some work that's been done on studying the hyperbolicity in the spherically symmetric case, which I'll mention. So in some sense, this has kind of emerged as like a benchmark modified gravity theory. Justin Ripley and Franz Pretorius actually a couple years ago looked at the hyperbolicity in the spherically symmetric case. For a given black hole mass, if you turn up the coupling too high, what they found happens is you get some elliptic region, that is where the hyperbolicity of the equations completely breaks down, and it starts inside the black hole horizon, where it sort of doesn't hurt you, but then as you evolve forward in time, starting with a vacuum black hole, it actually hits the horizon and exceeds it, at which point you can't continue the calculation anymore. And for lower values of the coupling, you still get this elliptic region. It just stays inside the black hole horizon. So since you can't evolve these elliptic regions, excision, just like Jeffrey was mentioning in his talk, taking a part of your computational domain and not evolving the equations there is sort of essential to handling this. So sort of once we go beyond spherical symmetry, things can only get worse with respect to hyperbolicity. But what we've sort of found is that this is the sort of generic failure move for these theories, that you have the excision surface coming in and hitting the black hole horizon. So now let me go on to some more interesting cases of black hole dynamics. So this is some results looking at the collisions of head-on collisions of equal mass binary black holes. So on the plot on the left, I'm showing you the scalar radiation as these black holes merge. This is sort of already scaling out the test field dependence on this coupling parameter. So you can see you get some nonlinear enhancement here. And you can also see that the magnitude of the scalar radiation at collision is actually comparable to the luminosity of the gravitational waves shown in this plot on the right. And you can also see that as you turn up the coupling, the merger happens a little bit sooner, and the gravitational wave amplitude is a little bit higher. And so we're actually able to collide black holes with coupling parameters that were sort of approaching the values where things break down even in spherical symmetry. And we also considered spinning black holes in different mass ratios and got similar results. So sort of the punchline here is that these methods seem to work quite well, even in the dynamical regime. So of course, the more interesting case is studying quasi-circular in-spiral binary black holes like we're seeing in gravitational waves. So here's a little animation of that. So this is the scalar field around an equal mass binary black hole. So the black holes develop a scalar charge and then in spiral emerge. And then the remnant black hole has like a larger curvature scale, so its scalar charge is reduced compared to the constituents of the binary. My student Max Corman and Justin have sort of been leading a study of trying to look at different binary black hole parameters and calculating the gravitational waves from them and see how the impact of these modified gravity terms work for this full shift symmetric Einstein scalar Gauss-Bonnet. So we're hoping to put that out soon, but here's a couple of early results from that. So on the plot on the left, we have a 3:2 mass ratio case. So in this case, because the black holes don't have equal scalar charge, you actually get dipole radiation. So as you turn up the coupling, you get the end spiral basically happens faster. And then this case on the right corresponds to a case with equal mass. So the dipole radiation is suppressed, but you can still see some dephasing later in the merger. And so sort of an open question that, these methods work well for sort of similarly large values of the coupling for the in spiral. But sort of an open question that we're still trying to address is how well they do for the sort of late stages of the merger, and whether or not there might be some breakdown of the hyperbolicity at sort of noticeably lower values of the coupling for the quasi-circular merger case compared to the head-on case. So right now we're seeing some hints that might be true, but it could also be just due to the fact that this breakdown is happening behind the common horizon, or there might be some better gauge choices that would alleviate this problem. So I just want to briefly mention that these methods can also be used to tackle other compact object mergers, in particular neutron stars. So one reason that neutron star mergers might be particularly interesting is that they can give rise to black holes that have masses of around 3 solar masses, which is small compared to other sort of known astrophysical channels for creating black holes. And all these theories sort of are most sensitive to the smallest curvature scales, so they have the biggest effects around the smallest black holes. So this is just an animation of one of those cases. So on the left, you can see the fluid density of the star, and the right, you can see the scalar field. So in this theory, neutron stars don't actually have scalar charge, so the scalar field is pretty small until they come into contact and merge, and then you form a black hole, and then you grow some scalar charge. So when these neutron stars come together and merge, you basically have two options. One is that they promptly collapse to a black hole. That's the case on the left. And the other is that they'll produce a long-lived remnant star. That's the case on the right. So in either case, you can see the gravitational waves on the top. There's very little effect on the in spiral. For the black hole forming case, sort of as the black hole is forming and ringing down, you can see some scalar charge. That's this bottom plot grows a function of time, and there's some small shift in the later stages of the quasi-normal mode ringing. So of course, this is at very high frequencies, well above a kilohertz, where current gravitational wave detectors have very little sensitivity. You can turn up the coupling, and this effect will increase, but you can only sort of increase it by a factor of 2 or 3 before you actually no longer have black hole solutions in the ethereal breakdown. So what's kind of interesting is that even if you don't immediately form a black hole and have a horizon, that the kind of curvature oscillations of the oscillating remnant star can actually source this scalar field. So this bottom plot shows the energy in the scalar field, just measured from its canonical stress energy tensor. You can see you get some oscillations here, and that's what leads to this little bit of dephasing you can see here. But what's particularly interesting is that we actually see evidence that the theory is breaking down if you turn this coupling up sufficiently large, and that this kind of nonlinear runaway might be happening even for values of the coupling that are still observationally allowed, given the observations of binaries that we've been seeing. So it seems like in either case, the results of a neutron star merger would kind of probe new parts of this parameter space. So again, like I said, this is all very high frequency, where the gravitational wave observations are prospects are kind of dim. So probably black hole neutron stars would be the more promising case here, which is something we're also looking at. So just to kind of conclude this part of my talk, there's still a lot of work to do. In particular, determining the domain of validity of these various theories and various choices of parameters and initial data. Something I didn't talk about is tackling the initial data problem in this theory, which would be another direction. But I think the sort of punchline is that we sort of now have the tools to answer questions like, what is the gravitational wave signal from compact object mergers, at least in these subclasses of modified theories. And then we can use that to compare to other approximate methods for treating modified gravity theories that can don't necessarily require you to have a well-posed theory as written down. And we can also potentially use these examples for benchmarking data analysis techniques that try to go after tests of GR. So in my remaining time, I just want to briefly discuss another way we can probe new physics, and that's looking for ultralight bosons with black holes. So normally when we think of looking for new particles, we think of something like the Large Hadron Collider. We go to higher energies. We look for more massive particles that are strongly coupled to the standard model. But it's interesting to think about sort of the complementary part of parameter space, where we have particles that are ultralight, but very weakly coupled to the standard model. So this would be things like the QCD axion or dark photons or other kinds of dark matter. And so it turns out that you can actually look for these ultralight bosons using black holes through a phenomenon called superradiance. So the point is that massive bosons, in contrast to massless bosons, can actually form bound states around spinning black holes. And if their frequency of the boson is less than m, where m is the azimuthal number of the cloud, times omega h, where omega h is the horizon frequency of the black hole, then they'll actually be in the superradiant range, and they'll actually take rotational energy out of the black hole, and the cloud will grow exponentially in time. And this exponential growth actually persists until the black hole has lost enough rotational energy that it's spun down towards horizon frequency, begins to match the oscillation frequency of the cloud. And this means that astrophysical black holes can actually be used as particle detectors to look for ultralight bosons whose Compton wavelength is comparable to the size of the black hole. And this is where this instability timescale is the shortest. And so at sort of saturation, you have this oscillating cloud around the black hole, and it will produce gravitational waves. So this is an animation from a simulation showing this nonlinear saturation and resulting gravitational radiation. So you can see the gravitational waves are pretty simple. They're almost monochromatic, and the amplitude is very slowly changing. Oops. So there's a number of different ways that one can think about trying to go and look for evidence of these ultralight bosons. One is just to measure the spins of black holes to look for evidence that they've been spun down through this mechanism. So you can measure black hole spins through electromagnetic observations of accreting black holes, or you can also try to measure them from observing the gravitational waves from binary black holes and inferring their spins that way. Another option is to try to directly detect the gravitational waves from these oscillating boson clouds. So there, one can imagine sort of doing blind searches for unknown spinning black holes with these clouds. You can either look for resolved sources or even a stochastic background of gravitational waves from a whole population of black holes undergoing this instability. So here's an example of that from some recent work using the stochastic background that one might expect from vector bosons and putting constraints on that with LIGO. So from this, you can see that an instrument like LIGO is primarily sensitive to ultralight boson masses kind of in the range of 10 to the minus 12 to 10 to the minus 13 electron volts. But sort of the downside of that is you're required to make assumptions about the sort of population of black holes there might be, in particular the masses and spins, in order to come up with these constraints. So another option is to specifically target sort of known spinning black holes. So a great way to create a newly born rapidly spinning black hole is to submerge two black holes together. So when we see that happen and we measure the gravitational waves, we have a very good idea of what the remnant black hole, what its properties are. And so that would sort of get rid of this need to assume some population of black holes. The downside of that is those events are rare and happen at larger distances. So even though in principle we might be able to see some part of parameter space, no one's actually done these directed searches yet. So these gravitational waves from ultralight boson clouds that kind of emerged as the other source that continuous wave searches are going after, in addition to mountains on neutron stars. And the gravitational waves are not exactly monochromatic. There's actually a small frequency drift. And so that's just due to the fact that the self-gravity of the boson cloud gives you a small redshift or negative frequency shift just due to the self-gravity. And then as the cloud dissipates, its mass becomes less, then the frequency actually chirps up. So that's in contrast to the sort of spin down that you might expect from a neutron star that's emitting gravitational waves. And so far we've actually, and sort of this frequency drift can be sort of a limit on how long you can continuously integrate the continuous waves from such a signal. So the typical search assumes that this frequency drift is very small, something like less than 10 to the minus 11 hertz per second. And we actually only sort of have so far in the literature Newtonian estimates of what this frequency drift is. So lately, my students Tal Shimei and Neil Simonson have been doing a fully relativistic estimate of this frequency drift. So you can see some example results here, where you can see that as you vary the mass of the boson cloud by order of a percent of the black hole's mass, you get an order 0.1% change in the frequency for this particular rather relativistic case. So I won't go to the details of that calculation, but we're basically putting that frequency drift calculation together with several other results that have been calculated using techniques out in the literature and trying to put that all together into a relativistically correct waveform model that will include both scalar and vector bosons. And the idea is that this will be sort of correct for the most relativistic signals. And basically, you don't want to lose any sensitivity in these searches to theoretical error. So the tentative name for that is super rad for that waveform model. I'm still trying to convince my students that that's an awesome name, but they'll come around. But yeah, so look for that soon. So in the last minute, I also want to mention that, so far I've just talked about ultralight bosons that interact gravitationally, but it's also interesting to consider what happens if you have some very small but non-zero coupling to standard model particles. So in particular, a natural model to consider is you have some kinetic mixing of a dark photon with our ordinary standard model photon. And so that you can think of it as that this this dark massive vector that would go through superradiance around a black hole would have some small coupling to electrons and positrons that would be parameterized by this parameter epsilon. So lately, Niels and I have been working with some particle phenomenologist friends to understand what would happen in this case. And so it seems like for the allowed values of this coupling, you can actually, through pair production, similar to what happens in a pulsar magnetosphere or around a relativistic black hole jet, actually create a plasma and then potentially power electromagnetic transient just through the boson cloud. So it's a bit tricky to understand the plasma dynamics of what happens, but Neil's been working on importing some techniques from simulations of the plasma dynamics of pulsar magnetospheres. And it looks like you might be able to get a rather bright transient out of this. And the interesting thing is kind of an analogy to a pulsar. You get this oscillating pattern on the sky that would be set by basically the mass of the boson, and the signal would decay as you'd expect through the gravitational radiation and dissipation of the cloud. So that'd be sort of a unique signal. So I think I'm out of time there. So I'll just put up my conclusions and just say that, yeah, I think we're arriving at a good understanding of both the non-relativistic and relativist regime of this black hole superradiance, and that some of these signals, particularly the very loud ones, might actually motivate new kinds of searches because their timescales are kind of intermediate between these very long continuous wave ones and rather short ones that you do for compact object mergers. So let me stop there and take any questions.
Thank you, Will. Questions? Jeffrey?
I just had a little technical question.
Yeah.
You mentioned that you had a problem with the excision surfaces hitting the apparent horizons in the binary black hole simulations that you were talking about. I just wondered if you were imposing a boundary condition on the excision surface or not, and if not, did you also have problems with incoming characteristic fields or not?
Yeah, so I mean, we typically, so in the result I showed you from the spherically symmetric case there, they were basically determining by looking at the characteristics where the equations went from being hyperbolic to elliptic, and then they're also determining where the sort of the edge of the trap surfaces were, and one met the other, and then so things break down. Typically, when they do the 3D simulations, we're not explicitly trying to monitor where things go elliptic, and we just monitor the apparent horizons and then try to excise as much as we can get away with of the interior. But then we basically know that if we evolve too far into the sort of strong coupling regime, then things break down, presumably for this reason.
Okay, thanks.
Any other question? Oh, Harvey, please.
Okay, thank you, Will. That was a great talk. I think just a question about the first part of your talk. So you mentioned this approach of if you don't have a well-posed formulation of the equations, you can try to solve the equations order by order in the coupling constant, and you said this gives rise to problems with secular growth. I was wondering if you could just expand a little bit on that and whether there's any hope of curing the problem with that approach.
Yeah, so that's not something I've worked on. That's mainly been like Masha Alkankova and collaborators. But yeah, I mean, I think what they basically found is that, for example, if you merge two black holes or something, basically as you, if you just look at the gravitational waveform at merger and look at the deviation you get from GR, as you start them farther and farther apart, you get larger and larger variations in the gravitational wave signal at a merger. And so, I mean, I know some people like Leo Stein have been thinking about some ways to potentially cure that by, yeah, I mean, we'll go, not really prepared to discuss the details of that. But then I guess another approach would be something like Louise and collaborators have done, where you try to introduce some auxiliary fields that would kind of drive your solution to the right one. But yeah, but I think just kind of as written, it seems difficult to make that order reduction approach work.
Thank you. I have a second question, if I may, which is so since you're now doing these simulations in the theory with the Gauss-Bonnet coupling, is your plan now to go on to start generating templates for comparison with gravitational wave observations?
Yeah, I'm not sure we're going to go so far as to making templates. I think it'd be nice to just have like a few waveforms that we trust, just a few examples. I think, you know, given the dearth of predictions from modified theories, just a few examples would be very nice. But yeah, it may or may not be worth investing the time in sort of building a whole template bank or something for one particular theory.
Good. Thank you, Harvey. We have another question here.
Oh, thanks for the interesting talk. I have several questions, so I will start with the one that most interesting. So can you go back slide to the dark photon and the pulsars?
Yeah.
So what kind of pulsar experiment are we talking about here? Is like the PTA or binary pulsar? Can you see more like here?
So this would be a transient that's basically powered by this oscillating boson cloud around a black hole. So just, you know, the oscillation period of that gives you this pulsation.
Why is specific for dark photon, not axion?
Well, yeah. So basically, you need to assume some coupling to, you know, to the standard model. So, you know, presumably you might be able to get some electromagnetic signal out of the axion by imagining some coupling there, but that's not the case we're considering here. Yeah. Yeah, so this is specifically imagining that you have this dark photon that has a kinetic mixing with the ordinary photon.
So this is done in the like PTA experiment or binary
so you're asking if this is like a pulsar timing array type?
Yes.
Well, not necessarily, no. I mean, I guess presumably this could happen around different size black holes. So you can imagine if you consider even less massive ultralight bosons, so kind of then you could have the same story happen around supermassive black holes. But you could also imagine that this happens around stellar mass black holes. But yeah, but this transient is basically powered by the boson cloud itself. Yeah.
Hi, Aaron.
Yeah, on this topic, you mentioned that this would be a transient event, but it seemed like this loss of the scalar field was quite slow. Do you have an estimate for how long this pulsar might be active?
Yeah, so I mean, it kind of depends sensitively on you know, how well the kind of Compton wavelength of your boson matches the size of your black hole. So the vector bosons can actually, in some extreme cases, decay quite rapidly, kind of an order of tens of hours or something. But then you can have a huge range that, you know, basically as you make the Compton wavelength larger compared to the black hole, then that falls off steeply as some power. So yeah, I mean, you could have transients that you could potentially see, you know, the decay of, or you could have ones that could basically over your observing time, but mostly look constant. And then for scalars, the dissipation timescales are much longer.
Okay, thank you.
So I have a couple of questions. So for the dark photon case, I guess you might have checked, like it doesn't change anything about early universe cosmology.
Yeah, so I mean, we weren't necessarily thinking of this as like a dark matter model or something.
Because
Yeah.
there were, I think, papers where they looked at how this would modify, for example, the CMB.
Mhm.
And I was wondering whether this has in like the parameter ranges that you're looking at have anything to say about the CMB.
Yeah, so I mean, I think people have thought about dark photons as like a dark matter model, but you don't necessarily have to think about that. I mean, these could be ones that you would, kind of just sort of create through this black hole superradiance.
Yeah, Will, actually, I can make a can I make a comment?
Sure.
Yeah, if you go back one slide. Yeah, like the constraint, like from 10 to the minus 15 to 10 to the minus 11 EV, that part is coming from like CMB considerations. Photons going into dark photon during CMB, which is the gray band right now. Yeah.
Okay.
Yeah.
I guess that answers my question.
Yeah, thanks.
Okay. And another question is, you showed these waveforms with this modified gravity waveforms that and how they. So I was curious, like, can this be mimicked by a change of binary parameters, but in just classical GR?
Yeah, I mean, that's definitely an important question to answer is, if you find some deformation due to your modified gravity, like how orthogonal is that to a change in parameters in GR? And so, yeah, we haven't tried to address that question yet, but it's an important one to ask.
Okay. Thanks.
Related to this, can you comment how that effect accumulate in the Fisher matrix in frequency, for example, Fisher matrix way sense?
Right. Well, for the specific theory I mentioned, like it does have a different frequency dependence because you get dipole radiation in a generic case. So I think that will be something that you expect to not be easily mimicked by just changing the parameters of the binary. Yeah, I mean, if you just see some effect like in the merge or something, that might be more more degenerate, but we haven't tried to do any complicated computation of that yet. We're still kind of at the early stages of trying to get a couple of example computations.
Okay, so we're going to wrap it up for the morning. Let's thank the speakers, the mic runners, and everyone that participated.